We are going to be looking at a displacement of a simple harmonic motion. But before we look at the displacement of a simple harmonic motion, let us first look at what a simple harmonic motion is or what it means. Any to and fro motion which repeats itself after a given time and whose acceleration is directed towards the equilibrium point and as well directly proportional to the displacement from equilibrium point is referred to as a simple harmonic motion. I'm going to take that again. A simple harmonic motion is a to and fro motion which repeats itself after a given time, whose acceleration is directed towards a fixed point or an equilibrium point, and this acceleration is directly proportional to the displacement away from the equilibrium point. That is what a simple harmonic motion is. So sometimes people tend to confuse between simple harmonic motions and ordinary periodic motion. So a periodic motion repeats itself after a given time, but a simple harmonic motion is a special type of periodic motion which does not only repeat itself after a given time, it is always a to and fro. And aside being a to and fro motion, there is always a restoring force. So if there is no restoring force, then you cannot describe a motion as a simple harmonic motion. So the motion will look something like this. From an equilibrium point, an object is displaced to the right. The object returns to that equilibrium position, that fixed point. It is again displaced to the left. It returns to this equilibrium point and goes to and fro, just in that manner. So we can have a maximum displacement here, which is called the amplitude. We also have a maximum displacement here to the left-hand side. So a simple harmonic motion will continue to repeat itself in that manner. There are several examples of simple harmonic motion, and I'm going to mention just a few. Loaded spring, when you suspend the mass from a spring and you displace it, the mass goes up and down and performs a simple harmonic motion. When you also have a test tube, a loaded test tube that is immersed in a liquid, it also performs simple harmonic motion. Another motion that is also simple harmonic is a swinging pendulum ball. So a swinging pendulum ball performs a simple harmonic motion. There are many other types like the physical pendulum, which we also call the compound pendulum. We also have another example of simple harmonic motion like the torsional pendulum. That we also have the bifilar suspension. Bifilar is spelled like this. We have bifilar suspension. Bifilar suspension. So sometime I'm going to do a video that will help us to explain the bifilar pendulum and how to obtain its period. We also have a cantilever beam. Cantilever beam. All these are examples of simple harmonic motion. We should take note that not all periodic or to and fro motions are simple harmonic. One good example I like to use is, let's say in a football training, you see two footballers passing the ball to each other repeatedly. So one may think that since that this motion is periodic, since they're passing repeatedly, that such a motion is simple harmonic motion, but it is not, because actually the force with which each person kicks the ball cannot be the same. So we cannot say that there is a restoring force. And the acceleration is not in any way directed towards a given position like we described for normal simple harmonic motion. Okay, but in this video, what we want to do is to obtain an equation for the displacement of a simple harmonic motion. And for us to do that, we have to bring up another definition or another description of the motion. This is actually not a very common one. It's actually not a very common one, but it will help us to determine the displacement of the motion. And in that case, I would like to describe the motion as a simple harmonic motion is a projection of a uniform circular motion on any diameter of the circle. A projection of a uniform circular motion on any diameter of the circle. When we use the word projection here, we are just talking about a shadow. So I'm going to do an illustration here real quick that will help us to understand that concept much better. So imagine that we have a circle. So consider that we have an object moving around this circular path. So let's say this is an object moving around the circular path. And we want to project the object motion on one of the diameters. In this case, I would like us to project it on the horizontal. This line is always the horizontal, so I just draw a horizontal line here. Now, consider that we have a flasher, we have a device that continues to flash light on the object as it moves. And then we decide to place the flasher somewhere here, since we want to consider the projection on the horizontal axis. So this is the flasher that brings out light. This is a flasher or a flash tube, if you like, that brings out light, or that brings out light. So as the object moves, we will notice that when I'm just going to place the ruler here to show us the position of the shadow of the object as this object moves. Now, when the object is here and light is coming from here, this is where the shadow will be. When the object moves to this point, so a point, say here, the shadow moves to this point. When the object gets to this point, the shadow will get here. If the object gets to this point, the shadow of the object will be at this point. And when the object gets to this point, the shadow will still be at the same point. Now we can reverse the position of the flasher and probably bring the flasher down here such that it keeps flashing light. And if it does, if the object gets to this point, the shadow will return to here. If the object gets to somewhere like in the center here, the shadow returns to this point. If the object gets to this point, the shadow returns here. So this can continue on and on. And we'll notice that the shadow of the object moves from here. So from here it moves up to this point, returns, and continues like that if you do not stop the object from moving. So the motion goes to and fro like this, and that is the perfect description of a simple harmonic motion, like we said much earlier. So let's consider projecting this on the horizontal axis, like I stated earlier. If we are projecting this on the horizontal axis, and consider for once that at a point where the object is, at the time where the object is at this point, we can actually draw a line from the center of the circle to join this point. And where would the shadow of the object be at this point? The shadow of the object will be here. It will be here. At that time, this object would have swept through an angle which is equal to theta. You will have swept through an angle which is equal to theta. And as we already know from uniform circular motion, the angular displacement, which is equal to theta, is calculated by using, the angular velocity, which is equal to omega, we usually use the letter omega, is equal to the angular displacement, that's theta, divided by time, just like we define the normal linear velocity, which is equal to linear displacement all over time. In the angular measure, we simply say that angular velocity is equal to angular displacement divided by the time. So from this equation, we can obtain theta to be equal to omega t. We can actually call this our first equation so that we refer to it when necessary. So look at what we have just done. And since it is the horizontal axis, we will call this place x. Simply call this place x. From the center to the end here is actually a radius, and that's the maximum displacement we can have. In the same vein, from the center to this point as well is also another radius, and that's the maximum displacement we can have. So we can simply call here A, since it is a maximum displacement. Even if we take a line from the center to any other part of the circumference, it is still equal to A, and that's the maximum displacement that the object can have from the center or from the fixed point. Now, this presents us with a very, very easy way to obtain the equation for the displacement of a particle performing simple harmonic motion. How do we do that? If you look at the triangle we have here, considering that this place is a right angle, if you look at this, if we take the cosine of this angle theta, remember that cosine means adjacent all over hypotenuse. So if we take the cosine, what we should obtain is cosine of theta is equal to x divided by A. We can actually simplify this further, and we get that x is equal to A cosine theta. We may call this our second equation. If this is our first, let's call this one our second equation. Let's call it our second equation. So looking at this, if we put equation 1 into equation 2, we will obtain x is equal to A cosine omega t. We will obtain x equal to A cosine omega t. If we like, we call this our equation number 3. Now, it is also possible to show that for particles that do not start from the beginning here and move around the circle, for particles that do not start from the beginning, it is possible to show that x is equal to A cosine omega t plus phi plus phi. Phi will actually be the difference in angle between particles that start from the beginning and particles that do not start from the beginning. Let's say a particle started its motion here. Let's say it started this motion here. If we trace this now, you see that the angle in question now becomes both the angle for the particle that did not start from the beginning plus the angle that has been turned. So in that case, theta will become equal to this angle plus this angle by the time the object moves up to this point. So this is the equation for the displacement of a simple harmonic oscillator in the simplest form.